very little change to there, but I could do that. And if someone says, I insist, I just want to take a single wavelength. The point being, you argue that point because, wait a minute, if we use every data point to get our kinetic analysis, it's bound to be better. Now, in this case, it's not so obvious because the data are all very deep. It's a single exponential over here. But if we go to the fellow that was brought up before, this guy, now if we look at this one, and I do the same sort of a deal, on the right, if we had this damn black screen, not more or less, that pisses me off no end too. If I move the wavelength, we see on the right, clearly the kinetics we get varies depending upon the wavelength. So just if you simply do nothing but take a bit of thought, you say, oh, look how that kinetics. So why would I sit at one wavelength when I might have lots of wavelengths? And the way this comes and goes and wiggles around suggests that I might get a better answer. And in fact, if I look here, there is no kinetics. I'm at an isobestic point. That is, it's hard to imagine that looking at this trace, having chosen that wavelength, or that wavelength, and chosen that trace, that's clearly not as good as if we consider all the data. And that's what our stratagem has been for 40 years or more. Use all the data to get the best possible kinetic answer. Good. Now, and when we do a kinetic fit using our methodology, that's what happens. All the data are considered, all the wavelengths. Goes up and down and flat and isobestic. The other point is, just looking at this, you can see right there, there's no change between the red and the blue, nor is there any change here. That is, we get so-called isobestic points, right there, for example. Now that tells us that probably there's only two species that are changing around each other, just by looking at it. But you'd only know that if all we had is the data we see on the right, that's all you have. You don't know anything except, well, it might be an exponential. So we get lots of wavelength, which is why we do those things. And anybody who says he wants to collect data at a single wavelength is stupid. I could say it to their face, that's a stupid thing to do when you're so much better. You're doing it to get an answer that's a quality, the best quality you can arrange. Use lots of wavelengths. Good. Now, the other thing that's now here's clearly a much simpler thing. There is no isobestic point. No matter what wavelength I go to, I see a similar looking kinetic trace. And I can look at it and say, oh, that looks exponential. This is rather boring. But it's still a three-dimensional thing. I collected it like that. That is, each kinetic data point is a spectrum. Good. Now, where we really start to get powerhouse is, so we can look at this. I'll do it and look at it in 2 dimensions. Good. Looks like an exponential, no isobestic point, no anything special. A very simple spectrum collapsing. This is a very blue dot. It's as blue as your cup over there. Mm-hmm. And we mix ascorbic acid with it, and the color goes away. Poof. This one happened to be done in a stop flow, and it took 1/10 of a second. However, we could arrange that this occurred over an hour if we wanted to, just by changing concentrations. So we can look at it and say, hey, that looks very exponential. Or, in fact, if you want to get particular, I can step over here, and I can go up underneath, and forget the fact that I have multiple wavelengths, and I'll go to the 2-dimensional fits. And I'll look at a fit at something here, A, changing exponentially, and it's headed towards zero, so it's bleaching. Is that, let me ask if these data fit that way. So I'll fit the data, these data, not those. So it takes a while, which annoys me, but we get now a very good curve, and it's an exponential. The difference between the fit, the math, and the data is quite a good flat line, although notice there's a very small suggestion that it isn't perfect. But it's very close to a clean exponential. Good. Now, write this down, in fact. We have here a rate constant of 2.7, or 27.45. 27.45. And the standard deviation is 0.0076. Or 0.00764.
You've written that down?
That's a noise measure. Good. Now, I'm sorry, Julie, what was that? So here we go back and I say, well, I remind you, we have lots of these curves. We just chose a wavelength. Clearly, if I'd have chosen this wavelength, I got pretty punk-looking data, but it should give me the same answer. But why not throw all the data into the fit, all the wavelengths? All right, and we have the capability of doing that since we have singular value decomposition. Now, so what I'm going to do is show these in 3 dimensions. Good. Now, and it has a very simple shape, but let's ask the question, how many spectral components are responsible for these data? How many players in the game? Now, if we look at this, we'd have to guess that it's going to be a single player, something with a nice blue spectrum. Again, as blue as your cup over there. And that color disappears into nothing as we react. Good. But let's ask our amazing singular value decomposition. So I'm going to, looking at the 3 dimensions, I'm going to hit SVD. Well, almost instantly, we have, reading from the left to the right, we see that in the leftmost eigenvector, in the time domain, the kinetic time axis, there's clearly a curve. Ah, that looks awfully much like our exponential. Probably it is. In the spectral eigenvector, there's a shape over the wavelength range. It looks awfully much like our spectrum. But more importantly, we see activity, curvature, only in the leftmost eigenvector. Then we see a flat noise here. That is, one can read that without equivocation, without hemming and hawing, without puzzling. Clearly, there's a single component involved in this process. There's only a single eigenvector, period. The machine very quickly, cleverly picked that up. We have 1, not 2 or 3, but 1. So we have to agree, and therefore I'll click here. Now, we have one player called A, and since there's only one, we're going to show you the possible mechanisms by which one molecule, one species, A, can be changed. It can do it as an exponential. It can be appear as a result of an exponential. And these physical processes I won't talk about now. But we have reason to think that its color, species A, exponentially disappears, because we can see it very cleanly. So let's ask the machine to, now here's where we start getting the neat stuff. Fit the kinetics, but this time use all the wavelengths, because you have them in those eigenvectors, not the one that I chose. So it will do that. Boom. Over here, it shows the exponential, or the curve, the DCIP, looks very much like that. Here, it shows the first order decay. Here, it shows the slightly imperfect, residuals. Here, it shows the standard, or the rate constant is 27.17. Slightly different from what we got before. And the standard deviation is 0.00
7.
755, 007. Yeah, 1, 2, 3.
Which is the same or better than what we got with fixed
It
wavelength?
should be better, it will
It is
be
better.
slightly better.
Is it better,
Yeah,
Travis?
it's better.
All right, good. Now, in this
Okay.
case, it's very
Slightly better
straight.
on the rate constant.
The rate constant, I would believe this one more. Well, what is it,
It
2717,
was 27.
45 or something, wasn't it?
Yeah,
Yeah,
27.
right. Well, I believe this one more. Now,